Okay. First things first, exam 2 has been graded. The exams have been published on Gradescope. The solutions are on Piazza. Please take a look at your exams. And if there are any regrade requests, send them to me by email within a week. And what I do is I respond to all the regrade requests at once, right? I do that all at once next Thursday. All in all, it was really good news. I have the statistics shown over here. So most of the class was above 80%. So in any case, there is nothing to really worry about. But there were some low scores between a 60 and a 80, but everybody else was above an 80. So I'm not concerned about people failing or anything of that sort. So I'm not going to be submitting any EWSS for this one. Overall, very, very good showing. So an average of what, 86. Of course, the distribution shows that it's going to have a higher median, 88. The least score was a 60. So that's all I have to show you in terms of statistics for the exam. And then if you have any concerns about grades, regrade requests within a week. Questions, concerns? Exam 2. We only have one more assessment left. What is that? Final exam. I think that's 30% of your grade. I may be wrong. I may be getting confused with signals. But yeah, so the final exam is left, which is going to be comprehensive. Okay, let's move on. Today we are going to be talking about introduction to operating systems. And for this, there is a lot of terminology that is going to come your way today. So what I recommend is reading chapter 1 of the textbook, which is Silberschatz, Galvin, and Gagné. The 10th edition is what you're following, but even if you followed 9th edition, you would be okay. So reading that chapter will give you all the nitty-gritty details about the terminology, because it's not going to be enough to lay all of those details out in class. So I recommend reading chapter 1 of the textbook for this particular lecture. Let's see. How many operating systems do you guys know? Everybody says Windows, Mac OS, Linux. All right. So these are all general purpose operating systems, right? So these are everybody, so general purpose. So good at almost everything, but not best at anything. General purpose. What are some other operating systems you guys know? Sorry?
Temple OS.
Temple OS?
Yeah.
What is that?
It's a variant of C.
Oh, okay. Sorry. Oh, I see. All right, that. Sorry? DOS? Oh, yeah, okay, all right. Man, your generation knows DOS. That's a very encouraging thing. So disk operating system, right? DOS, one of the very, very primary, like those were the first set of operating systems that came out. So of course, yeah, MS-DOS, Microsoft disk operating system. What else? The ones that you guys use on a daily basis while walking. The phone ones, yeah, the Android and iOS. Android, believe it or not, occupies 70–80% of the market share. I didn't think that it was that high, but yeah, apparently it is. So those are what? Those are smartphone operating systems. What is the difference between, say, a Windows and an Android? The size of the operating system is different, right? One is meant for general purpose application. The other guy is meant for embedded applications. I need you to be small. I need you to be quick. right? So I want the response time to be really, really fast, but I also want you to do all the other things, like how do you manage files? How do you manage mass storage? How do you manage protection? I also need you to do all of those things, but I want you to be very, very small, right? So I'm going to take some aspects of the graphics, right, and then associate that with the functionality and trying to keep that operating system small. So yeah, the smartphone operating systems. How about other than that? So we talked about general purpose, we talked about smartphones. What are other operating systems? You guys heard of a type of, go ahead. Right, so what operating, so this is like a younger brother of Android, right? Like even smaller than what you have. Is there a name for that? WatchOS, yes, absolutely. So for Apple, there is a WatchOS. I don't think there is a, there's another name for, there may be, but I'm not aware of it. Right, so even smaller, right? Even smaller in terms of size, just do the bare minimum, do the basic functionality, whatever is required by that watch. How about robot operating system? So if you guys are interested in control systems, and if that's the area that you want to go into, then one operating system that you will have to sort of learn and know how to, you need to be familiar with is robot operating system. That is, has a lot of automation features. So that's going to be, that's ROS, you call it. What else? Real-time operating system. So for embedded applications, I want things to be very, very quick. So real-time operating system, RTOS, is like a blanket, right? Within that, you have all of these watchOS. Any small-sized operating system would fall under that. Anywhere where you want your response time of the operating system to be very quick in real time, that would qualify as a RTOS, real-time operating system. What else? What operating systems do you see on really high-end oscilloscopes? You guys have used like very expensive oscilloscopes in a lab. Not the analog discovery, not those. The higher end ones, $100,000, $150,000 ones. Yeah. So most of them run Windows, but they don't run full Windows. They run instrumentation OS. So some smaller version of Windows is run on that. But the interface is exactly the same as you would expect on a desktop Windows, like click start button and everything like that. But behind the scenes, it's not as big as the general purpose OS. So essentially what I'm trying to say is there are going to be operating systems for a lot of these scenarios, right? General purpose, smartphones, watches, instrumentation, robots. How are they different? Well, they're different in terms of their size, capabilities, the functionality is different. What is important to them is different, right? As a general purpose user, it's like, okay, do a lot of things, but you don't need to be an expert at something, right? That's kind of a general purpose view of that. So I think that was a good discussion about operating systems in general. What do we know? Where does it sit? Well, it sits right here. It is an interface between computer hardware and all the other users. So what do you have? You have, say, Bennett is working on a MacBook Pro, I think. So he has a Mac OS that is running on his laptop. That's one user. One user that is interacting with one operating system to run many applications, right? So there are several system level applications or user level applications that are currently running on his laptop. So we are talking about Bennett running a compiler, assembler, a text editor, word processor, WebEx, whatever that is, which is a program on his Mac OS. To do what? To be able to access the computer hardware, right? What are the resources does he have access to? He has access to CPU, maybe multiple cores, right? So that's one resource. What else is the resource here? Memory and I/O devices, right? Input/output devices, keyboard, mouse. So these hardware resources are being shared between all the programs that are running on his laptop, right? You see, all of these application programs are trying to use the same CPU, same memory, same I/O devices. So there has to be someone in the middle, a traffic cop, to say, all right, I'm going to allocate this particular user to this particular resource to this particular process. I'm going to allocate this much main memory to this process, right? So that is an operating system as a resource allocator. So that's one of its main purposes, to be able to make sure that there is fair and efficient allocation of hardware resources to the users, right? Now, I'm saying users, but those are multiple programs. But you could also have a scenario where there are multiple users trying to go for the same CPU, the same hardware resources, right? So for example, picture a server, right? The server, you're logging into it on in a distributed environment. So on a network, you're trying to log in and you're trying to access the hardware resources that are present on a server. Why is that? Well, I don't have 100 cores on my laptop, but there's a server that has a lot of processing power, right? Lots of hundreds of loosely coupled processors. How do I make sure that all the people in my company, for example, or my lab or whatever in my group gain that power? Well, I can set it up as a network operating system. I can set up a distributed environment where anybody can log in to the same operating system and use those resources, right? So that's user one using the same operating system to share a particular hardware resource, right? So it could be several users that are running their own applications on a host operating system to share the hardware resources. And the operating system, without it, what is going to happen? If operating system was not there, then what would happen? Bennett's applications would have to fight within themselves, right? Word would say, no, 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 I need the memory now. Chrome would say, no, 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 I need the memory. I am more important, right? The application programs are going to be fighting with each other for resources. We can't have that. So what that puts pressure on is inter-process communication, right? So if we had some mechanism in place in which all the processes that are running had a way to communicate with each other so that they can gain access to the resources, yeah, that would work. But that's not going to be realistic, right? That's not feasible. So you just have one layer of operating system that sits between the programs and the hardware, does the allocation. So it's an intermediary between the users, or if they're just one user, between the programs and the hardware. What are the goals? Well, it should be easier to schedule user programs, and it should make things easier for the user, right? It should make problem solving easier. That's how you choose an OS, right? Maybe one thing could be how good it looks, right? But once you get past that, you're looking at how easy it is for me to use a particular OS so that all that scheduling and all that resource allocation can go on very, very conveniently, right? Right? That's how you choose it. Oh, in Microsoft, so in Windows operating system, I need to do this, 4 steps to be able to accomplish this task. But in Mac OS, I can do this by simply clicking this and this, right? So that's a convenience for me. So I'm going to prefer Mac OS to do that particular task. So what they're trying to do is make the life of the user easy, and they're also trying to execute and schedule user programs. Scheduling user programs is probably one of the topmost sort of tasks for an operating system, right? So there are multiple processes, right? He has several processes. Can I find out what are the processes that are currently running on Bennett's laptop? How can I find that out? Mac OS. How can I find that out? Windows, what would you do? Task manager, Control Alt Delete. Task manager, what will you find out? For each process, what will you find out? Go ahead. Activity monitor for the Mac OS, yes. But what will you find out within that? Go ahead. Allocation of the CPU resources, what else? RAM allocated to each process, name of the process, what else? Graphics processor, GPU allocations. You will also find its process ID, right? Each program, when it becomes in the execution stage, what is it? It's a process. Each process gets assigned a process ID. That's how it gets identified within a list of the processes. Some processes are system level, system applications. Some are user applications or simply user programs, user processes, right? So you have kernel space and a user space. All of those will show up on the activity monitor or the task manager, whatever you have, they will show up with a process ID. Now, the goal is, how do you schedule them, right? So will any process go first? The operating system is going to be there to say, all right, you got the resources, you can execute, then I'm going to assign it to them. Then I'm going to assign it to process 3 and so on. So scheduling processes is one of the primary tasks of OS. And we'll talk about how does the computer schedule it, CPU scheduling algorithms. We'll talk about a few of them. That'll be an interesting lecture. Next, make the computer convenient to use. And we talked about this, right? It is not going to be okay for me to use an Android OS on a desktop hardware, right? That's not convenient. So make the computer convenient to use. That's another goal of the operating system. Protect the computer and the users from what? From bad users, right? What could the bad users do? Well, they could mess up user space, right? So they could write programs that overwrite over user processes. That's a problem. Or a bigger problem is some bad users could write programs in the space of the OS, right? They could go change the OS. We don't want that, definitely. Or some, I wouldn't call them bad, but notorious users could do this. They could write programs in such a way that they always have control over all the resources, right? I'll write an infinite loop so that all the resources, even though I'm not using it for anything useful, all the resources will always be with me, right? They will never go away from me. So there should be ways that should be implemented that don't allow for this kind of thing to happen. A simple way could be implement a timer for each process. If a timer expires, the control goes back to the kernel, right? But yeah, protecting the computer from the users, from the bad users, and also protecting other users is a job of the operating system. So how do you allocate memory for each process? How do you manage privileged mode and non-privileged mode? Assigning read-write access to processes is a job of the OS. Use the hardware efficiently is the main goal, right? Limited hardware, many programs. I'm going to try to do that assignment efficiently. That's the whole point. So OS, you can view that as a resource allocator, or you can view that as a control program. So as a resource allocator, we have talked about that, managing all the resources. How should I assign hardware resources to different processes that are currently executing, getting executed by the CPU? So decides between conflicting requests so that there is efficient and fair resource use. How does it decide? Maybe it decides based on the size. Maybe it decides based on the priority of the process. Maybe it decides based on how long has it been since you got the resources, right? Something like the least recently used algorithm, but for processes getting the CPU, the hardware resources. So the operating system has to do that. Based on some scheduling algorithms, it's going to do that. Let's see. Operating system as a control program controls execution of programs to prevent errors and to prevent improper use of the computer, right? So for example, some mathematical error happens, divide by zero error happens. You are going to have to send out an interrupt. You are going to have to denote that some error has happened. How do you handle that? Well, there will be an interrupt service routine, ISR, for each type of error, each type of interrupt. So you go there and then you handle that, right? The operating system has to monitor that, right? Oh yeah, divide by zero happened. Where do you look? You look at the output of the ALU, right? The ALU output has to suggest that, oh yeah, the user tried to divide by zero. The operating system looks at that and then says, okay, I'm going to start running a interrupt service routine because of the user doing that. So that's how it prevents errors or handles errors. Prevent improper use, we talked about that, right? Not allowing people to write over OS pages or other pages, meaning talking about the contiguous block of virtual memory. So OS pages are there in the main memory. There are pages even for process 1, process 2, process 3, and so on. I shouldn't allow process 1 to interfere or write or read in the space that belongs to process 2. Maybe I want that, right? If I want that to happen, then I will allow it. But generally, I'm not going to allow that to happen. Especially processes trying to read or write OS pages, especially write OS pages, right? The one program that runs all the time, what do you call that? The core of the operating system, the kernel. Everything else is either going to be a system program that ships with the operating system, or it's going to be an application program that the user installs on the OS. Can you guys give me like an example of a system program, something that is shipping with the OS, but it is not part of the kernel of the OS? Good. A file manager is one example. Yeah, absolutely. So system programs will be, let me see, if you go in your activity monitor or your task manager, these will be processes that are running, but you didn't start them, right? Those are just running. Those are sort of system programs or system calls are essentially CPU is working on something on behalf of the operating system. Not on behalf of the user, but on behalf of the operating system. That's a system call. So all of those are going to be running, and you can track them in your task manager. But when you see them, you would notice, oh yeah, I never started this. It is just running there. So that is your system program. And then, of course, application programs, right? Chrome, Word, WebEx, whatnot. All right. What are the system components for an operating system? There are many on this list. These are just like 7 of them. There are other aspects to an operating system as well. Process management, and we'll talk about each of them in detail. Not a lot of detail, but we'll briefly talk about it today, and in the subsequent classes, we'll go into each one of them. So process management, main memory management. Process management has to do with what? How do you create new processes? How do you delete processes? How do you suspend and resume processes? All of that is going under process management. How do you manage memory space in your RAM? How do you do data storage management? What is your protection system? How are you protecting your computer and users from bad users? How are you managing a distributed environment using networking, right? How can users try to share loosely coupled processors over a network? And what does the user interface of an operating system looks like? And it's very simple to see, right? Like I've logged in, I see a desktop view. Is the desktop view a graphical user interface the only interface for an OS? Can you guys tell me what is the other alternative to interact? Oh, go ahead. Command line interface, right? CLI. So I think you are a DOS command line interface person, Richard. Old school. Right, so command line interface. So you could access that on the terminal in your Mac OS. You have command prompt in Windows, and you will have this command line interface for not only for OS, you will have it even for application programs. So wherever you don't want to import all the graphics, but you just want to execute certain commands, use the command line interface because you're getting away from the heavy importing of graphics, which can be very stressful on your host OS. All right, so that's your user interface, a desktop view with GUI or just a command line interface. All right, let's talk about process management. What does it include? What's a process, first of all? Process is an active program, right? A program that is just there. Do you have Word installed? Do you have it running? So Word is a program that is not a process right now on Bennett's computer, right? So if he starts Word, then it becomes a process, right? Because now it is requesting for resources to be allocated to it. I need some space in the main memory. I need to be able to access my keyboard and the mouse as the user types, so that I can project it onto the screen, right? So all of that is not happening right now because it's passive right now. It's not active. An active program is going to be a process. And obviously, you will have a scenario very common where you have multiple processes that are running that are trying to say, all right, I need the CPU resource. I need the CPU resource. The activities of the OS, operating system, that are involved in process management. What are they? One, process creation and deletion. Can I create new processes and can I delete new processes? Who is going to provide that mechanism for the user to do that? The OS, right? You can obviously create a process, double click on Word and it'll launch. You can obviously delete a process as well, right? And you can do all of these things, not just in the desktop view. You can also do all those things using the command line interface. Now, process suspension and resumption. Why would you ever want to suspend a process? Well, maybe there are not enough resources available. If enough resources are not available for a process, maybe you would need to suspend it. Now, once the resources become available, then you can resume it. Again, there is competition for that, right? Resources have become available. Which process is going to get it? Higher priority process, bigger process, user process, kernel process, which one? So the operating system has to sort of manage all that, decision making for which process gets to get it. Provisions, mechanisms for what? Process synchronization. Multiple processes, as they are working, you allow for them to communicate with each other. And if you want that processes to communicate with each other, what you can do is you can program pipes, which you can use as ways to pass information between processes, which fall under the category of inter-process communication. So we'll talk about how we'll talk about specific programs we can write where we create processes and then create pipes so that processes can communicate with each other. One simple way of creating processes is using a fork system call. Have you guys heard of a fork system call? Unix. So fork is a Unix system call where if a current process has a fork call, it creates, so that's in a parent, right? So as before the fork call, you have a parent process running. As soon as you have a fork, then it splits into the same parent that it was originally and a child process. So you create two processes. Once you create two processes, parent will have whatever the original program had. Child will also have the same thing that the parent had. But now what you can do is replace the child's process with something else. So now you have got two things that are running in parallel, right? So you have got a parent process and you have swapped out the child's process with something else, some other executable. Now, if you wanted that parent and child to communicate with each other, suppose they're trying to do a same task, but there has to be synchronization, right? Did you do that step? Let me know if you do that step so that I can start this step, right? So if they want to communicate, how can they communicate? You have to program pipes. Pipes are ways of allowing processes to communicate with each other. IPC, that's inter-process communication. Again, we'll talk about that as well in detail. Moving on. Main memory management. What are we trying to do here? We are trying to keep track of which parts of memory are currently being used and by which process, right? How is the allocation for the DRAM, the physical memory, being done for processes and for OS? All of that is being tracked by the OS. And the OS also decides which processes to load when the memory space becomes available, based on priority, based on size, based on privilege, which one, right? OS decides that. So the OS is allocating and deallocating memory space as needed by the processes. Again, we'll talk about this as well. How does the operating system accomplish main memory management? One of the core ideas we will look at is free space management, right? When there is free space in the main memory, how do you allocate space to a particular process when free space becomes available? Now, free space is not always continuous in the physical memory. You will have a block of memory free here and here and here. It will be fragmented, right? So how do you take a fragmented memory space and allow some part of that main memory to be allocated to a particular process, right? So you can set it up as a linked list, and you can do a lot of things in that. We'll talk about how we do that in free space management later on. Next, data storage management, and there are a couple of items over here that fall under the category of data storage management. One is file system management, the other is mass storage or your secondary storage management, and there is also an I/O subsystem. We'll talk about all these three aspects of data storage management. One, file system. What is that? How does the operating system allow the user to create files and directories, right? So file creation, deletion, directory creation, deletion, all of that going under file system management. Next, primitives to manipulate files and directories, right? So we are talking about, let's see, mkdir, right? Make directory command. That's a primitive that supports creating a directory, for example. So the operating system has to support primitives that allow you to manipulate files, say copy files and remove files and all that, files and directories. Next, ensure storage consistency and durability of what? Files creation, files and directories onto a storage, either your secondary storage or something that is slightly above that secondary storage, maybe a solid state drive. Next, mass storage management. How do you manage free space? How do you allocate storage for each process? How do you schedule processes to be able to write to a disk? Right? Disk is slow. So how are processes going to be able to, say, save things to disk or read things from a slow hard disk? You have to schedule that. Disk scheduling, also part of mass storage management. Decides, managed, kept track of, monitored by the OS. Next, I/O subsystem. So these are, this is a subsystem in the OS that manages communication between the computer and the I/O devices, mouse, keyboard, whatever you have, printer, monitor. All of these are your I/O devices that you hook up to your computer, right? So in your I/O subsystem, you can have buffering. The buffering is what? Each device. What do you need for an operating system to be able to communicate with a device? What do you need? As a bare minimum, what do you need? Nowadays, you don't even have to worry about that. You plug in and it gets installed. Driver, right? So a device driver is like 10, 15 years ago, it was a pretty serious thing, right? Not all devices, when you plug in to your host computer, they would just automatically install. You would have to actually go find your device driver and install. Most of the devices would come up with a compact disk where you put it in and install the driver. Not anymore, right? Now device drivers get pulled off from the internet and get automatically installed for almost everything. unless you are talking about something that is, say, user designed and prototyped. If it is in the market, then it pulls it from the internet. But what does it have? Well, it has a local buffer, right? Inside that device driver, the device driver has an I/O controller, which is also called as a device controller. But along with that, it also has a local buffer. It is that local buffer stores information that is going in and out, right? So if it's keyboard, the information goes to that local buffer for that device driver, and then eventually goes to the memory of his computer, from the keyboard to the local buffer and to the memory there. So that's buffering. That's allowing for buffering. Caching, again, that's a very, very small space close to the CPU to allow for very, very quick access. Spooling, what is that? A queue, right? So spool is, you guys have heard this term, spool. For printers, you have seen this. When you log into, say, RPI network printers, when you have to access them, you must have seen that you actually log into a spool of printers. Yeah. But no, so when you put requests, they go on to the spool, right? A spool is essentially a queue. New requests for the printer, that goes onto a spool, right? And then in the order they came in, they will get serviced. So for example, there's a printer, right? Everybody wants to print to it. Is it going to just print all of them at once? No. It's going to keep a spool, it's going to keep a queue of the requests, and it's going to respond in the order the request came in. Next, the I/O subsystem also has a general device driver interface that is for all devices in general, but it will also have drivers for specific devices. You guys have you guys ever had to do that in the last 5 years or so? Yeah. You have? Update drivers, okay, but oh, okay. Yeah, yeah. So, but that was older computer or older device? Was that an older computer or was it an older device? Both. Yep, absolutely. Yes. Yeah. So, right. But if you had to talk about Windows 7, current versions of Mac or Linux, I don't think, well, in my opinion, I've not seen that problem, at least for products that are in the market, not specialized products that are, designed by individuals. Talk about general made available to the public. I have not seen people install device drivers, which is a pretty big deal. Even if you have a mouse would come with a CD. You guys know CDs? Okay. I just wanted to check. You guys don't know floppies. Okay, you know. What's that? You know, you are old school. You are not. You know DOS. You can have a T-shirt that says "I know MS-DOS." Yeah. All right. I don't have a floppy disk, but yeah, that's when we started using computers. Used to have that 5.5 inch. Then we went to 3/4. Oh, that was a big revelation. Like that was, wow, can we do this with the 3/4 inch? Yeah, so I remember that time. All right, coming back. So device drivers, right? So you would have to install device drivers, or the OS would have a generic device driver interface. Next, responsibilities for the I/O subsystem. You interface with the system components, manage the devices, allow for data transfer to happen between the I/O device and your memory, and detect when that I/O, the input-output operation gets completed. All of those are responsibilities of the I/O subsystem. How do you implement a protection system? Well, The need for that is because multiple users are trying to share the same resources. So they're trying to share the CPU, the main memory, the IO devices. So let's take an example of trying to share the same memory space, right? Processes, say process 1, should not be able to read or write things that are in the process 2 memory space unless it has access to it, unless it is meant to be. In general, each process has to have their own memory space, which is not overlapping with any other process. Now, in the virtual memory, you can think of it as a continuous space for process 1. But in the physical memory, it would be frames in the physical memory that may not be continuous, but they are meant for process 1 only. Right? They're only accessed by process 1. Let's see. Protection. What is that? A mechanism for controlling access by the programs, processes, or users to the system and user resources. Who gets access to the system? Who gets access to the CPU? Who gets access to the memory space? All of that falls under the category of protection system. It should distinguish between authorized and unauthorized use. If there is some process, if there is some memory space that is allocated to the OS and a process is trying to read or write to that, that is unauthorized use. And the operating system should signal a trap addressing error. That's a memory violation. Specify the controls to be imposed for that, right? So every process gets the read-write access. Do you have read access to this space? Do you have write access to this space? And we'll talk about some ideas how you can implement that protection. Provides a means of so not only setting up the rules, but also enforcing how that how the operating system responds to violation of those rules. So essentially, that is trap addressing error, and it usually results in suspension of the process that initiated that violation. Next, networking and distributed systems. So this is what I was talking about. You're in a group. You don't want to use few processors on your local computer, but instead you have high intensity tasks that you want to run on a distributed system, right? So you have this particular resource available. You have a collection of loosely coupled processors that is available, which is your distributed system. You all want to use that. How can you use it? Well, there has to be some connection through a communication network, maybe a LAN or maybe a wireless LAN, whatever that may be. You should be able to have access to those loosely coupled processors. So if processors are connected to a communication network, then you should be able to do it if you have the rights to it. A distributed system is providing users access to various system resources. So this is what typically happens, right? Like if you are a part of a research group at a university, or you are part of a group at your company, this is what will typically happen. All your high intensity tasks will be executed by a computer that has a lot of processors that people will log on to, use it, and then relieve those resources. So that can happen through a communication network. The access to a shared resource, it allows for computation speed up, right? I can't get it on my computer locally, so I'll get it on a distributed network. So I'm going to gain computation speed up because of that. Increased data availability. I can have a big mass storage on a server. Any users can log on to using a communication network and access information over there. So I'm not limited by the data storage on my local computer anymore. Enhanced reliability. Why is that? When you have something that is that powerful and you have a lot of storage associated with it, you will not have one copy of it. You will have multiple copies of it. You will have redundancy built into the system because that's a critical point, right? So because of that, you have increased the reliability, which is not going to be a feasible option for users, right? I can't expect Bennett to buy another computer just because he wants to keep the data very safe. He wants to keep the IO devices. He wants to, I can expect him to maybe get another hard disk to put all his data over there. Maybe he can back up his data to make that he can increase as a reliability. But I can't expect a whole group of people to do that. So instead, what do? I just make another copy of that distributed system connected on a communication network, a redundancy built into the thing that matters the most in that case. Next, user interface, and we talked about this a little bit already. Command interpreter, command line interface, or the graphical user interface, right? This is the face of the OS. So what does the command line interpreter have? It is essentially a program that reads and interprets control statements, like a Unix shell, like a terminal, like a command prompt. It is either a part of the kernel or it is a special program that the user installs. What do? You run all these commands, right? Run, remove, move, copy. All of these are primitives that are supporting some aspect of the OS. Maybe to copy files from one to the other. That goes under the data storage management, to create processes, and so on. Anybody remember how do you create a process in, say, Linux, in a Unix or Linux-based shell? Just create a process. How do you do that? I forget. All right, don't worry about it. I thought I had that off the top of my head. Graphical user interface. Everybody knows this. Start a computer, this is what you see, right? What do you see? For the people at least in the class, that's what you see, right? Your desktop view. What does it have? Windows, mouse, you will be able, that's the face of the OS that we are used to, right? Developed by Xerox, popularized by the famous Apple Macintosh. Now, if I have this, right, let me ask you this. If you start your computer and it is over here, WebEx is saying update, but I'll not. It's over here, right? Is it going to do anything now? Is my OS going to do anything? It's just going to sit there, right? That's it. It's just going to sit there until I do something, right? Until I move my mouse, until I click the keyboard, until I unplug something. Until I do something, my operating system is going to be a program that is just there, right? It's just running, but it's not doing anything, right? Which essentially brings me to the point that operating system in general is interrupt driven. So you have to, the user has to interrupt it, only then it responds to all those interrupts, right? That's the game of the OS. If you don't do anything, it's just going to sit there. So when you start your computer, the Bootstrap program is going to get loaded, and the operating system is going to occupy your main memory, and that is it. It is just going to sit there until interrupts happen, either interrupts by users or by the kernel, right? Let's move on here. So that's your system operation. Where does it start? Operating system starts with a Bootstrap program. Bootstrap program is not the OS. Bootstrap program is the door to the OS. It is also called as the firmware. Where does it reside? It resides in the ROM, right? Read-only memory. So a non-volatile memory, so that it doesn't I don't have to worry about the power, right? It's a non-volatile memory. So what happens when you start a computer? Bootstrap program gets loaded into the main memory, and then the operating system starts running, right? So the firmware gets loaded into the memory. So that's your Bootstrap. I can just highlight that, maybe write in ROM called firmware. Now, after the OS gets loaded into the main memory and now it is running, it's just going to wait, right? It's just going to wait for events to happen. Events are usually interrupts. Interrupts are also called as traps, interrupts are in two categories. One is a software interrupt, the other is a hardware interrupt. So when I move a mouse here, that's a hardware interrupt, right? But something that is happening inside a system call, or while I was executing a program, there was a divide by zero, or you tried to access some memory space that you were not meant to. All of those fall under the category of software interrupts. But if you are messing around with a keyboard, mouse, a hard disk, all of those things are going to fall in the category of hardware interrupts. Software interrupts are also called as traps or exceptions. So until you interrupt the OS, it is just going to sit there waiting for events to happen. And as soon as interrupts happen, what is it going to do? It is going to launch interrupt service routines, right? So it's going to respond to interrupts by executing interrupt service routines, ISRs. Now, a problem that could happen is this, right? Multiple things are interrupting at once, right? Or right after each other. How are things going to happen? How are we going to take care of things if I'm typing and I'm moving my mouse and I'm transferring files to a hard disk? I'm trying to do all of those things at once. How is that going to be maintained? How is that going to be managed by the OS? There are two main options. One is synchronous I/O, which essentially means I will wait for that operation to complete, and only then I can start the next one. The other one is asynchronous I/O, which is whatever requests I'm getting, I will just log in into a device status table, and I will take care of those at a later stage. But I'll keep accepting requests, and I log it into a device status table. We'll talk about those two types of I/O in a little bit. So how do you handle interrupts? Until interrupts have happened, until events have happened, the OS is just sitting there. But once they do, we need a way to handle those interrupts. Briefly, it is executing the ISR. For each interrupt, there is going to be an interrupt service routine. And for each interrupt service routine, there is going to be a program counter that points to it. Right? So there will be an address of the first instruction in the ISR that will go into a program counter for that particular interrupt service routine. How does it start? Handling of interrupts. First, you save the machine state and the instruction that you are currently executing. You got interrupted over here, right? CPU was working on this particular instruction. You got interrupted over here. You save the machine state, right? So you save any temporary variables if you have, or whatever you have worked on so far for a particular process that you were working on, save that state and the instruction address that you were working on, disable any new incoming interrupts, transfer the control so that you can work on the interrupt service routine or the interrupt handler. Usually this is device specific ISR, right? For each device, it's going to be a specific one. This is essentially a vector of addresses in memory, one for each ISR, right? So how are you going to service or handle interrupts coming from a keyboard or a mouse? They're all going to be different, and they're all going to be vectors of addresses in the memory. And they're all going to be disjoint, right? One for each device. Once you get done with your interrupt service routine, then you restore the CPU state. Go back to the instruction at which you interrupted it. All of this brings me to that same point that I made initially. The OS is mostly interrupt driven, right? It is just waiting for events to happen. Until then, it is just going to sit there, not doing anything. All right, let's move on to just a illustration of how interrupts are going to work. On the top, these are two timing diagrams. So the x-axis in both of them is indicating time. On the top over here, we are monitoring CPU. And on the bottom over here, we are monitoring the I/O device, any I/O device. It could be a keyboard, that's an input device. It could be an output device as well, so like a monitor, that's an output device. Now, suppose the CPU is working on a user process, right? It's just working on some user process and is doing that over here. And at some point, some IO device requests for a data transfer. So the way an IO device is going to request that is by when the CPU writes a few registers into the IO controller or the device controller that will initiate IO. So that's when the IO request was made. The CPU is continuing to work on that user process. It's not stopping. What happens at this point is the IO device was idle before, but once the CPU writes those few registers and initiates that IO, we are going to switch that IO device from the idle state to the transferring state. So now the data is transferring from what to what? From the device to the local buffer of that device. Local buffer is going to be part of your device driver. Next, data transfer takes some time, right? Sometimes it may take longer, sometimes it may take shorter. But after the transfer gets done, we are going to indicate to the CPU that, yes, I am done with the IO completion. Now you service the routine, which means the data has been transferred to the local buffer. Take that data and transfer it to your memory. So CPU is going to service that. CPU services are going to be interrupted so that they complete the IO. Now that particular completion could take short amount of time or it could be slightly longer. But the question is, while the data transfer was going on, right, we didn't stop the CPU working on that process. The CPU continued working on that user process until the data was ready in the local buffer and the interrupt service routine was going on, right? The transfer was getting completed. Once the transfer got completed, only then the CPU services were interrupted. So we have those two options there, synchronous IO and asynchronous IO because of that. We'll talk about that in a slightly more detail in just a minute. So you have an IO device. Each IO device is going to have an IO controller, also called as the device controller. Now the CPU will initiate that IO by writing some specific registers in the IO controller for that particular device. The running process, which is the CPU is currently, right? So how is this working? The CPU is currently working on some instructions. Those instructions, one of those instructions was to initiate that IO. So it wrote those specific registers. It is again continuing to work on that process. So the running process can either do this one option or two. One option is synchronous IO, which means wait for that IO to complete and then continue working on the running process. If you do that, then you can have only one IO at any given time. Only the keyboard, only the mouse, only one IO at any given time in that case. Because during that IO transfer, you're not allowing any other interrupts to come in. Only one IO at any given time. The second option is proceed anyway. You have got interrupted, right? You have initiated a IO. Don't stop running the current process. Continue. That's called asynchronous IO. But because you are proceeding anyway, you're allowing for more requests to come in, right? More than one IO at one time, you're allowing that to happen. So if a lot of requests come in, you're going to have to manage that with some table. So we need a device status table to keep track of all the IO requests that are coming in. So there is good and bad in both of them, right? Synchronous IO, the bad is only you can only service one IO at any given time. The good is you're only focusing on that one of them, right? You're only focusing on that one guy. The good with asynchronous IO is you're able to take in many requests. The bad with that is they get completed at a later time, right? Because you have just logged those entries into a device status table so that later you can complete the IO. So both of the, so how does a device status table look like? Well, over here, we have several devices. Say, for example, card reader 1, a line printer 3, a disk unit 1, 2, and 3. The device status table is also going to monitor the status of each of these devices. So for example, it could be in an idle state, or it could be in the busy state, or it could be in the not functioning state, right? Busy, idle, and not functioning for each of these devices. So as the requests come in, you see this device line printer 3, it is busy. So if a request comes in, it is just going to put it on a spool. It is going to keep track of that request. Request for line printer, starting address is given, and the length of that request is given. And done. We have just logged down the request in a table. Now, once that line printer 3 gets done, it was busy. When it is available, when it is ready, it is going to service that request. And for example, over here for disk unit 3, it was busy. And then we have some requests made here, some requests made here. One is for a file. What is this? To read a file between this and this address. And then over here, we are writing a particular file starting at this address for this amount of length, right? So this is for disk unit 3, reading a file, writing a file, all of these. It was busy, so we are not able to do it right away. We just put in the request in the device status table. So when disk unit 3 becomes available, then it will try to complete first request first, and then the next one next. Right? So, but we are going to need a device status table because all these requests, we just allowed for many of them to come in, log them into a device status table, and then service them. As opposed to no need for a device status table. As soon as the request comes in, service it, then move on. Like you have to complete the I/O before you move on. That is synchronous I/O. So the two views are shown over here. Synchronous on the left, asynchronous on the right. So in synchronous, what happens? You are in the user space. You are currently running a user process. As soon as you get a request for an I/O, the control goes to the device driver, goes to the kernel space where the data transfer can happen. It is going to take some time for that data transfer can happen. During this time, the requesting process is just going to wait. It's not going to move. It's just going to wait for that I/O to complete. Once that I/O gets completed, through this interrupt handler, we are going to indicate to the user process that I have completed the I/O. Then you can resume your the process that was waiting can resume. That's synchronous I/O. But in asynchronous I/O, what are you doing? A user process initiates, go through the device driver, because we are going to know which device I'm trying to access, right? Directly go to the hardware, move data from the hardware to the local buffer of that hardware. No, don't do that, right? Over here you were doing that. Don't do that here. Just log this entry into the device status table and immediately come back to the requesting process. You don't wait for the data transfer to get completed. Data transfer can happen at some other later time. And whenever it gets done later time, you can let the interrupt handler tell the user process that I completed that particular I/O, so that that request can be removed from the device status table. So in this guy, in the synchronous I/O, this is the main difference really, right? While the data transfer is going on, the requesting process is waiting. Over here, we don't do the data transfer. We simply log the information into a device status table, and then you return control back to that user process. Continue working on that. All right, so that's your difference between synchronous and asynchronous I/O. Let's move on to hardware protection. How are we going to make sure that users are protected from bad users? The operating system is also protected from bad users. We have some strategies over here that we will lay out. Sharing, it improves utilization. Very intuitive, right? We have a limited number of hardware resources. If we share them, that's going to increase utilization. But it is also going to require a mechanism to protect users or protect the operating system. You can have a bunch of layers of protection. The first layer could be using a dual mode operation, which means you can either be in the user mode or in the kernel mode, authorized versus unauthorized, or I should say privileged mode versus non-privileged mode. On top of that, you can have protection built in for IO completion and CPU. The third protection can be for memory violations to be tracked, memory protection. So let's take a look at each one of these things. Dual mode operation. A mode bit added to hardware to indicate the current mode. There is a hardware bit that monitors which mode a process is in currently. It could be kernel mode, which is your privileged mode, in which the mode bit is 0, or it could be in the user mode, where your mode bit is 1. This is the non-privileged mode. Now, when an interrupt or fault occurs, the hardware switches to kernel mode. You see this? This is a view here. This is the user space in the gray area. This is the kernel space that is highlighted in the blue area. The user process is currently executing, right? Some word is currently executing. And there is a system call that is made. That a system call is what? A system call is some task that the CPU has to complete on behalf of the operating system to support one of its components, main memory management data, some task that is within the list of so many tasks for an OS. One of those tasks has to be completed. Who is going to complete that? A system call is going to be complete that. So system call, you can view that as something that is being done on behalf of the OS. So there is a call for this. There's a system call made. We are going to change that mode bit from a 0, from a 1 in user mode to a 0. We go into the kernel space. We are in the privileged mode now. Then we are going to execute that particular system call. We are going to return to the user space, and while we do that, we are going to change our mode bit from 0 back to a 1. And then we are going to continue working on that particular user process that you are working on. So by having this particular mode bit, 0 or a 1, a particular process can keep track of which space you are in. The OS can keep track of which space the process is in. And if the process is in the user space, it is in the non-privileged mode, right? It is going to have to go to the kernel space to be privileged. Privileged instructions can only be, because privileged instructions can only be given in the kernel mode. So if you want to execute a particular system call, you have got to be in the privileged mode. Kernel mode, privileged mode, monitor mode, system mode, supervisor mode, there are several names for that particular mode when a particular process is in kernel space. So that's a dual mode operation by using a mode bit. This is sort of a block diagram view of the same idea. Let's see that system call to complete some IO. There is a user space over here, gray. We are executing instructions in the user space for a particular process. There's a system call that is made at this particular line. We are going to change the mode bit. We are going to transfer control to whatever that IO function is, right? In the kernel space, we are going to complete that IO. From here to here, that's where your IO function is written in the kernel space. So you execute that. Once you're done with completing that IO, you return back to the kernel space. So that is indicated over here. Come back to wherever you started. So where does it start? So system call, process needs IO. Go here, start executing. Choose the specific IO function, execute it, right? Perform the specified function, then return to the user mode, and you're back to where you started. Next, IO protection. How are you going to use the privileged instructions can only be issued in the kernel mode. All the IO instructions are privileged instructions. So whenever you're trying to do IO, input-output devices, talking to an IO device, those are going to be in the privileged mode. So you've got to be in the kernel mode for that to happen. So that's how we are implementing protection for the IO devices, because we are only doing it in the privileged mode. Next, CPU protection. How are you going to make sure that the CPU cannot be misused by a particular user? So for example, a user says, I will write an infinite loop, keep the resources, keep attention of the CPU with me all the time. I'm never going to relieve it. How can you fix that? Well, implement a timer, right? So if you implement a timer that returns control to the OS periodically, then you get away with that particular problem. So periodically issuing an interrupt. The timer, once it expires, it initiates an interrupt. To service an interrupt, where do you go? To the kernel space, right? So the control goes back to the OS because of that. That's how you can prevent users from using resources unlimitedly, infinitely. Next, how do you protect memory spaces? So the short answer is you use base and limit registers. So on the left over here, we have the view of memory, main memory. Say you have certain space allocated to an operating system. Then you have something for process 1. Let me just number 1, 2, and 3, right? So this is how it looks like in memory. We have base and limit registers. Those registers contain start address and something that is related to the stop address for a particular process. So for example, if you look at process 2, the base register that is corresponding to process 2 contains the starting address for that particular process, starting address. Then the limit register actually contains the length of that process, right? So this length is in the limit register for that process, P2, which essentially means base plus limit will give you the ending address. How are you going to use this base and limit register? Well, let us suppose that there is a process 1, right? Process 1 is trying to access the memory. It's either trying to read or write to memory. And the address it is reading or writing to is, for example, 40,000, right? No, not 40,000, 400,000, right? 400,000, if process 1 says, I want something to read or write at address 400,000, you use the base and limit registers for process 1. Base register for this tells me that it has to be more than this value. It's not, it is, yeah, 400,000, it is more than this value. But the limit register for process 1 is over here. Your address that you requested, it is actually greater than 300,000. It had to be less, right? It is greater. So that's a memory violation, trap addressing error. So that's, you cannot allow that to access, right? So by using comparators and using this base and limit registers for each process, you can make sure before you give access to the memory, you can make sure whether a particular process is authorized to do that or not. So that's what you have, your base and limit registers. Each process is going to use base and limit registers to protect a region of memory. So how does it look like? It looks like this, right? So you have your CPU. CPU is currently working on, say, process 2, right? Say P2. CPU is currently executing process 2. And we know the base and limit registers for it, this guy and this guy. First, it is going to say the address that you want to either write to or read from with respect to the memory, is it greater than or equal to the base register or not? If it is yes, then good. Then you can move on to the next comparator. If it is no, you have a trap addressing error, memory violation. So interrupt service routine, handle it, usually with a suspension of process 2. Next, if it is yes, then you go and check for whether it is less than base plus limit, which is the ending. If it is still yes, then you allow access to the memory. If it is no, then again, the same thing, trap addressing error, service routine, suspension of the process. So by using these two base and limit registers, you can sort of protect regions of memory from processes that are not authorized. Let's see. All right. That is all I have for you guys today. I'm going to stop recording. You guys can work on the activity. I will see you guys on Monday.